Many times we discover something about the world, like gravity, and later learn the important math that goes behind it. Other times we discover something seemingly random in math, and later find important applications in the real world. And that's the case with the Riemann hypothesis. If we can solve this problem, it has important applications in other areas of math, and even how fast your computer runs. So let's get started. To start, let's take any positive number, let's call it n, and output the sum 1 over 1 to the n plus 1 over 2 to the n plus 1 over 3 to the n, on and on. For example, if we let n is equal to 2, we have 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and on, which is approximately 1.644. For input 3, it's approximately 1.22. And this is called the Riemann zeta function. But there are two problems with this function. First, as we make this input higher and higher, the output gets really close to 1 but never reaches it. Also, if we plug in a number like -1, we get a sum that just doesn't make sense, 1 plus 2 plus 3, and that just goes to infinity. To get around this, we can analytically continue the function by reflecting it across a line of symmetry. Doing so gives us this very nice graph on the complex plane. The Riemann hypothesis is to find when the values output 0. But you might be wondering, who cares? Why is this so important? How does finding when this graph is 0 help with anything? Well, first, we'll be so much closer to finding a formula for prime numbers, which has been a source of study for mathematicians for over 2,000 years. Let's see how. Let's define f of n as 1 over 1 to the n plus 1 over 2 to the n plus 1 over 3 to the n, and on and on. Now, if we multiply both sides of the equation by the second term, 1 over 2 to the n, we get this. If we subtract this second equation from the first and factor, we get this equation. Now, if we multiply both sides by the second term again and again, you can notice on the left-hand side we get the prime numbers in the exponents of the fractions, and on the right side we get our zeta function. So, if we can understand the right-hand side better, it'll give us crucial insights into prime numbers. Solving this problem also has important applications to quantum computers, which run up to 5 times faster than our normal computers. So as you can see, this problem is immensely important to understanding mathematics and physics. And if you can solve this problem, you'll get a nice sum of $1 million too.